Hello everyone, my name is Katerina Pirkovets and I'm a PhD student in IME Group in Leiden University Medical Center. And today I want to tell you about Formula 1 tactics in robot-assisted surgery. Please be advised, this video includes explicit surgical imagery and viewer discretion is recommended. Robotic surgery is a field of precision, control and complexity, where every movement is tracked in high resolution. But this isn't unique. Another domain has mastered the art of using motion and data to drive performance, Formula 1. In this presentation, we explore how concepts from Formula 1, like sector analysis, kinematic profiling, and performance optimization, can be applied to advanced robotic surgery. Just like in racing, smarter systems in operating room can react in real time, correct for human errors, and ultimately save lives. AI doesn't replace the surgeon, but empowers them with insights, accuracy, and safety beyond human capabilities alone. In Formula 1, it's not just the driver, it's the entire pit crew, engineers, and data analysts working in harmony. Similarly, our approach to surgery involves a team: surgeons, nurses, anesthesiologists, and data scientists. This synergy between technology experts and the end user, the surgeon, is critical for translating data into meaningful surgical guidance. Just like in Formula 1, surgical robots generate high-resolution data streams. You can think of robotic instrument movements as car kinematics, tracking speed, acceleration, position, and precision in real time. This data lets us analyze how surgeons navigate each step, much like Formula 1 teams study driver performance through every corner of the track. With vast amount of data, we can improve performance, safety, and consistency, not by guessing, but by measuring. Our study objective is to use raw movement data, the actual motions of surgical instruments, to identify the different steps in a robotic procedure. In this study, we focused on 4 videos of robotic prostatectomy performed by expert surgeon. The procedure is split into 10 standard steps. And for clarity, each step has been assigned a color, which will repeat in the further images. You can think of procedural steps of the surgery as track sectors in a race. Each sector requires a different strategy, pace, and maneuvering technique, just like in surgery, where each step demands a distinct set of motions, tools, and focus. The robotic arms is tracked in 3D space and synchronized with endoscopic video. We start by converting the robot's instrument movements into digitalized tracks. Such tracks for forceps and scissors from the video you can see on the right. This gives us a spatial and temporal map of the operation, the surgical equivalent of tracking the location of the car. We intuitively understand that surgeons operate differently at each step of the procedure. Interestingly, these behavioral shifts are also reflected in the kinematic data. By analyzing this data, we can separate surgical steps based on their unique kinematic signatures, using machine learning algorithms. To validate our clustering, we assess how distinct each step is, using silhouette scores. This helps us identify which steps are clearly different, highlighted yellow in a heat map, and which ones overlap, like steps 1 and 4, shown in more blue heat map squares. We also pinpoint the key metrics driving these differences, such as time, distances between instruments, spatial positions, and a specific instrument used. As a result, we gain more understanding into the surgical procedure workflow and make a step towards automated step classification, based solely on instrument kinematics. Like in Formula 1, kinematic data is predictive and powerful. In robotic surgery, metrics such as time, instrument positions, inter-instrument distance, and tool selection can define what step is occurring. With this knowledge, we can begin to guide training, optimize performance, and even enhance safety. I'd like to acknowledge our collaborators and funding partners who made this work possible.